It is my pleasure to introduce Dr. Ben Brown. He works as a research fellow in the Quantum Information Theory group at the University of Sydney, where he is mostly working on quantum error correction. Before going to Sydney, he was a postdoctoral researcher at the Niels Bohr International Academy in Copenhagen, and he also received a doctoral prize fellowship at Imperial College London for his doctoral research. And then without further ado, I'll cede the floor to Ben. Take it away, Ben.
Okay, thank you very much. Let me put my slides up. Okay, so this is my work. Well, it's not just my work. I'm going to give my talk when my slides stop changing on practical quantum error correction with the XZZX code and Kerr-cat qubits. So this is actually a culmination of a lot of projects. A big question all my research is about quantum error correction, more or less. And quantum error correction is about how do you take all the pieces, all the things we can make in a lab that are never quite perfect, and put them together in such a way that we can make really almost completely noiseless logical qubits that we can run in a quantum computer. And the things we actually build are what we call quantum error correcting codes. Quantum error correcting codes they use a redundancy of these physical qubits, and we work out the quantum error correcting code works in such a way that we can make special measurements, that tentacle stabilizer measurements, or just error detecting measurements, where we spot the qubits that are going wrong and we can fix them before it becomes a big problem for the computation. Now, we still don't have big quantum computers that solve useful algorithms. There are still lots of problems in quantum error correction that need fixing. And well, one of the problems is it's just really hard to make good quantum error correcting codes that deal with all the noise in the qubits we can make in the lab. People are trying really hard to make really good qubits, but getting them below the threshold where quantum error correction is really going to work is hard. Okay, now, so I've got quite a lot of collaborators and quite a lot of papers on here. I'm going to focus on just one or two of them, but let me give the bigger picture. So a question we liked asking in Sydney quite a lot was, well, how can we make quantum error correcting codes better, given some more knowledge about the system we're actually building them out of? So the problem was the way quantum error correction in the field has progressed for a long time has been with where we just assumed a very generic noise model, and we just asked how good all the codes we can ever imagine making at dealing with that particular kind of noise. And well, the thing is, we actually have to make our quantum error correcting codes out of something, and maybe we can do quantum error correction a lot better if we know what's going wrong with that particular kind of qubit. Maybe we can come up with a better kind of quantum error correcting code this way. So what we were thinking a lot about was how do we, first of all, how do we learn what our qubits are doing and what's good about them and what's bad about them, and then how do we make a code to compensate for their shortcomings? And that was a hard problem. There's lots to optimize there, because you can change the code and you can change the kinds of qubits and all sorts. So what we said was, let's make the problem a bit easier, and we'll say, let's just suppose the qubits that we're working with experience some bias noise. Let's just suppose, because it's quite common with qubits, that they experience dephasing more so than they do bit flips. Hello? So is somebody? All right, then I'll talk to you later. Well, we have, so we came up, this program of research at Sydney with these researchers at the bottom here, David and Steve Bartlett, Steve Lemire and Pablo. We came up with a series of research led us to come up with what we called the XZZX code, and that was really good at dealing with bias noise. I'm going to say quite a lot about that, and that eventually led into more work with Shruti Puri and the other people you can see at the top here, Andrew and Arne Grimsmo, because there what we did is we took this XZZX code that's very good at dealing with bias noise, And we took some bias noise qubits, which Shruti had been working out, which they're actually building at Yale. And yeah, we put them all together and we found that that seems like a really good proposal for actually building a quantum computer. So a lot of the tricks we needed to come up with the XZZX code, it kind of led from this work with Don Williamson that we started, a bit earlier on. I'll say a little bit about that, but not too much, because that's a bit out there, maybe. Now, this is actually a really hard talk to give, I think, because there's lots of expertise about the lab and the quantum optics behind the qubits. I'm not an expert in those things, and so I'm probably going to make some mistakes. But I think by telling you that, you're going to pay a bit more attention, because, yeah, I'm going to need your help to error correct the things I say, and that's something, yeah. Do pay attention anyway. Now, so as I said, we're interested in what kind of quantum error correction can we do if we know something about the noise other than absolutely nothing. And what we want to assume is our qubits are dephasing. Now, luckily, in parallel to us doing this work in quantum error correction, in Yale, for instance, they were working on these Kerr-cat qubits. Again, this is not my expertise, so let me just try and say a little bit about this. So these are superconducting qubits, and they have with a Kerr nonlinearity and a 2-photon driving, and they just did this experiment. Well, these are the experimental parameters they put in. There was a Kerr nonlinearity strength and a drive strength of 1060 megahertz, and well, what can we say about this? They led what they found in the experiments were T1 times something like 15 microseconds, and this is ongoing work. They're currently working on doing gates with these kinds of qubits, I know, and they're hoping they can get to T1 times around 100 microseconds, which I understand to be quite good. Okay, so this is, I'm moving on. Now, so this is a cat qubit, though. This is what they built. This is the physics and the quantum optics of what they built. They have, they can engineer in that experiment I just described, kind of, you can read about. They can engineer this Hamiltonian, where they have a Kerr nonlinearity, which is this term with Kerr nonlinear strength of K, and they also have this 2-photon pumping term. And what's nice about this is the ground states of this Hamiltonian are what they call cat states. So cat states, they're just coherent. They're just coherent states. And but in the ground space, there are 2 coherent states, plus or minus alpha. You can easily rearrange this Hamiltonian to see why that should be the case. So coherent states are just they're the eigenstates of the bosonic annihilation operator, and this is more or less a qubit. They're not quite qubits because they're not 0 and 1 and orthogonal, but we can roughly say alpha is about 0 and negative alpha is about 1. And if we make alpha quite big, then the overlap between 0 and 1 will be exponentially smaller than alpha. So this is the kind of qubit that I'm imagining. We can prepare coherent superpositions of plus alpha and minus alpha in phase space. Right, now, as I said, why are these so exciting? These qubits are nice because they're very biased. It's very difficult to accidentally flip a 0 state into a 1 state. Because if we make alpha very big, then the likelihood of plus alpha being flipped over to minus alpha is quite small. The one thing that can go wrong, though, is that photons can be lost. So this number alpha, well, the modulo of alpha squared is roughly how many photons are in one of these coherent states. So the bigger we make alpha, the more likely they are to lose photons. And a photon loss, if we prepare our qubits this way, is a bit like a Z error, which is the kind of dephasing errors that we're more worried about than the bit flip error. So these are really perfect qubits for what I was describing, bias noise, because dephasing errors are bad, and they can happen reasonably often, but bit flip errors are suppressed. in this number alpha. So what was really nice so what was going on while we were doing all this work in error correction is Shruti Puri in this reference at the bottom, she was coming up with even bias preserving gates. So it's all well and good having a qubit that is well protected against a certain type of noise, like Z noise. But sometimes, well, if we actually want to use these qubits for doing something useful, like quantum computing, we need gates as well. And so some kinds of gates, gates are just unitary operations that we act on this qubit subspace. Now, some types of gates are diagonal, and they just preserve noise. They map Z errors onto Z errors, and other types of errors aren't a problem. But other types of gates that we also definitely need, they have off-diagonal elements, and they're not obviously bias preserving. You might imagine trying to do some gate with some off-diagonal elements, like, I want to do a Pauli X unitary rotation. That's got some off-diagonal terms, so you might expect that won't just lead to Z errors, it might lead to other types of errors as well. And so all the bias you have in your qubit memory is lost because you're doing an off-diagonal type of gate. Okay, but the thing is, these cat qubits, these are, we're actually encoding qubits in a higher dimensional space, a boson. And what they showed in these papers at the bottom is that you can actually do a bias preserving NOT gate and a bias preserving C0 gate. Now, the C0 gate is a bit more complicated, so I'm just going to describe the NOT gate, but the physics is quite similar. So what they showed was you can change the phase of your Kerr drive. I hope I said that right. And what happens then is you take this number alpha and you modify it by this phase, this e to the I phi. Now, if you change this phase, then what happens is this 0 state rotates around to the 1 state, and this 1 state rotates around to the 0 state. So that's effectively an off-diagonal NOT gate. But the point is, all the way through this rotation, as you rotate phi, you always kept your two lobes, your two coherent states, well separated in phase space. And so they were always quite robust against bit flips. And the only thing you were worried about was dephasing errors, which are still photon losses. So this is great. What we have is these things called Kerr-cat qubits. They're very biased, and we can even do lots of gates that are bias preserving. Well, now, in fact, what we're going to see is that we don't need that. You can do quite well without a bias preserving gate. That's important too. But what I just want to do is I want to motivate one particular kind of qubit that does do all the things, that has all the properties that I'm kind of hoping for. Okay. Now, right. So I'm now going to talk a bit more about error correction. And I'm going to tell you how the XZZX, I want to give you some intuition for the physics behind the XZZX code and why we get such good thresholds and why bias noise is so good. Why it's particularly good at dealing with bias noise qubits. Okay, so let me just start by talking about the repetition code. The repetition code is a classical error correcting code. You can think of it as a list of bits all in a row on a line. I want them to be on a line. And these bits can take values plus or minus 1. You can think of them spins in plus or minus 1 states, where we can say the +1 value means a 0 and the -1 value means a 1. And the way we'll encode a bit is they just repeat each other. So if we want to encode the 0 state, all of the bits are in +1. And if we want to encode a 1 state, all of the bits are in -1. Okay, so as I said, error correcting codes are supposed to be able to deal with some of these. Some of these bits are supposed to get flipped, and we're supposed to be able to deal with those. My slide didn't change. Okay, so what we need is a way of detecting those types of errors. So what can we check with a repetition code? We can check that a bit is equal to the value of its neighboring bit. So that's what we call a parity check. So whatever state we've encoded with all the states in the +1 value or all the states in the -1 value, what we know is if we take the product of two adjacent bits, they should always be +1 because You can work through that. Okay, so if that's not the case, so this is what I would call a stabilizer. And if this isn't satisfied, then we know some errors have occurred. So I'm gonna go on to the next slide and see what happens when errors have appeared. So here is my repetition code one more time, but on the red bits, errors have happened. So there's an error here and here and here, but not here and not here, and so on. Okay, so what we can see is if we compare the values of, say, these two bits, they're both the same. So nothing's detected as being bad there. And on these two red bits, they're both the same as well. So if we compare those two, they look fine. But if we compare this term with this term, or this bit with this bit, then they don't agree. They have odd parity. So that defect, that stabilizer is lit up. It gives the -1 outcome, not the +1 outcome. So I'm going to call that a defect. A defect is shown up because of those errors have violated that stabilizer. And that happens in a few places on this string. It happens here because these two bits are in odd parity, and happens here for the same reason, and so on. So the way I like to think about this, and what's really useful, or what's a useful way to think about this, is actually these errors appear like strings. For every error, the bits that are violated live on the ends of a sequence of flip bits. So here we have just one flip bit, and it creates defects on its two adjacent sides. And well, here I've drawn, a sequence of flipped bits, and it's created defects at its endpoint. So I really want to think of this sequence of flip bits as a string, and the defects live at the endpoints of this string. And so what we need to do is error correction. So the task is to look at the endpoints of these defects and try and bring them back together in a way that everything is corrected. So in the case of the repetition code, there are two ways we can do that. We can look in between the defects on this red patch and flip all the red ones, or we can look at we can flip all the bits on the black spins, and that will cause a logical error. We'll have flipped all the wrong ones, and that will have taken the logical state to the other logical state due to the errors, and then the correction we try to apply, that's bad. We don't want that. But providing the bits don't experience too much noise, we're in good shape. We can still correct it. And okay, so how much is that noise? That's what I call the threshold. And you can kind of see with the repetition code, if you add more and more bits and the error rate is quite small, then you're going to succeed at correcting this with higher and higher probability. But as the bit flip error rate goes up, it's going to get harder to do that successfully. And well, when it gets to 50%, that's the threshold you would expect with a repetition code, because you would need more than half of the bits to flip to typically cause a logical error. That's how error correction works with the classical repetition. Okay, that's classical. We're just doing classical bits, but what we really need are quantum codes. So the one that everybody is trying to build right now is what's called the surface code. We can't make quantum error correcting codes in 1D very well because there are now two types of noise. There aren't only bit flips, there are also phase flips. If we want to
I have a question. How dependent is your threshold for the surface code on something like your decoding algorithm?
Quite dependent. We have pretty good. We have quite a lot of good quantum error correcting codes. Quite a lot of good decoders now for the toric code, and the threshold is quite good compared to the optimal that we might expect. Now there are other things you have to worry about as well, like how fast does it go, and so sometimes we want to trade off performance and how many errors it can deal with how quickly it goes, because there's quite a lot of information. You can measure these stabilizers on a superconducting chip. You can measure these stabilizers at like microsecond speeds. So
and then the classical computation might go slow.
That could slow things down, and then you have to worry about lots of other kinds of things, like getting the information out of the fridge and then back into the fridge on how to correct it, and that's a problem that I don't understand as well as I ought to. I don't need to say too much about the toric code just now, though, or the surface code. I say those things synonymously. All you need to know is the problem is still the same. If you're satisfied that in the 1D case, errors just look like strings and defects live on the endpoints, and the task is to bring the endpoints together, then the surface code is just the same. Error correction is the same. Errors look like strings. Defects live at their endpoints. And the task is just to pair them all up. So yeah, thanks for your question about decoding, because yeah, so one way we can do that is with what we call the minimum weight perfect matching algorithm, where we give, so the minimum weight perfect matching algorithm takes a graph with some edges and returns a matching, which is where all of the vertices have just one and only one edge touching them from the original graph. And if you you can use the minimum weight matching algorithm to tell you the right way to pair up the defects. And well, I'm going to say a bit more about this in a moment, but the point is, because the problem has now gone from a 1D problem to a 2D problem, the threshold, it's a more complicated decoding problem, and the threshold goes down. And in fact, it gets a little bit harder than that. So what else can happen in this in a more realistic situation where you actually have to think about the circuits you use to measure these stabilizers is sometimes the measurements give you the wrong answers as well. Like your photon detector was supposed to do a click and it didn't, or something like that. Well, then this decoding problem that I've tried to paint is just trying to pair up the endpoints of strings. Well, it now becomes a 3D problem. So what you do, what does everybody do when you're not trusting of your measurements? You repeat your measurement over and over and over again until, you repeat your measurement over and over and over again. And what you do is you compare two time adjacent measurements. So you say, well, okay, so here is a stabilizer of the toric code that I measure at time t minus 1 at time t and t plus 1. And let's say the error happened at time t. Well, if we compare this measurement outcome to that one, this measurement gave the wrong outcome, so it's going to be different from this one. So we say there is a defect there. And the same will be true if we compare the measurement at time t to the time t plus 1. So it'll be different here as well. So you can see again, there is a string. And
do you choose your number of time steps to be the same as the code distance?
Yeah, that will be your code distance. You need to run it for, really, you're just going to measure and measure and measure until all your computations are done, though, or that piece of surface code is done doing it.
But you probably need to take a certain chunk of time and then decode and then keep going. Yeah,
you can do it like that as well. You
but you can
might run it for a really long time, and you might break the decoding problem up into blocks. That's right. But the upshot is with these strings when there are measurement errors, you can think of measurement errors as being string errors in the time direction, and we still have the physical errors from this 2D plane. So error correction is just strings in this 3D space-time. And yeah, then we have to, we take a big block of this 3D space-time, we put it through minimum weight matching again, and the logical, hopefully all the strings get paired up correctly and no bad things into the code. Okay, so I've explained a series of increasingly difficult problems. And here is the picture I really want to paint. And this is going to I want you to remember this, because this is why the XZZX code gets you what it gets you. So as I said, with the repetition code, it's not hard to imagine that the threshold is about 50% error rates or a half, and this is a one-dimensional problem. If I try and error correct the 2D toric code, and I assume all the measurements are perfect, and I use this minimum weight matching algorithm, the threshold is about 10%, which is a lot smaller than 50, but it's bigger than 3, and 3 is the threshold you get if you try and error correct in 2+1 dimensions when there are noisy measurements as well. So you can see as you look at more and more increasingly difficult decoding problems, the threshold goes down. And so typically what you will have heard is a 1% threshold. That's what people have been shooting for a long time. It's actually a bit less than that. That number 1% comes from what they call the circuit error model, which is a bit like this 3-dimensional problem I described, but it's where you account for every single circuit element to measure those stabilizers, and you put an error rate on those individually. This 3% number comes from when there are
some assumptions here too, right? You're supposing that the errors you have are within the computational space. Because if you have things like
Yes,
leakage,
yes, I've not.
things can trip up.
I haven't. You can go deeper and deeper and deeper. I haven't assumed that qubit leakage can happen, but people have ways of dealing with that.
Okay.
Yeah, that's true. Yeah, thanks for your question. Okay, so you can see it's getting harder as the dimensionality gets bigger. Now, so the XZZX code, let me just say what that is. It's just like the surface code. So the surface code has some stabilizers, just like the repetition code did, and I described those in a bit more detail before. Now there are qubits that live on the vertices of this square grid, and the surface code has two kinds of stabilizers: Pali X stabilizers that live on the black faces, and Pali Z stabilizers that live on the white faces of this chessboard-like grid. And so the Pali X stabilizers are responsible for spotting the Z errors, and the Pali Z errors stabilizers are responsible for spotting the Pali X errors. And altogether, yeah, you can see like there are about as many Pali Z stabilizers as there are Pali X stabilizers. So all these stabilizers are doing their best to spot the errors that they're responsible for. Now, this seems a bit daft if you have bias noise, because like, why would you have half of your stabilizers searching for Pali Z errors if you're not, searching for Pali X errors, bit flip errors, if you don't expect them to happen very often? You want something different. And what we found was the XZZX code was really good at that. It's just like the toric code, except all of the faces have a XZZX stabilizer on every single face. So you get that from just applying a Hadamard to all of these green qubits on the original surface code. So everything, all the nice error correction, all the quantum gates, and all of the fault-tolerant quantum computing we know from the surface code follows over onto the XZZX code just by applying this Hadamard gate. Everything is locally equivalent up to a local unitary rotation. So it's really nice and easy. But what's this done? Like physically, the way you can think about this working, or why is this helpful, is because all of those sort of lazy Pali X stabilizers that were busy looking for errors that nearly never occur, I've now made them responsible for some of the Z errors as well. So all of the stabilizers that weren't doing very much are now looking out for the common types of Z errors. Meanwhile, the stabilizers that were looking at the XXXX stabilizers that were responsible for 4 of their neighboring qubits experiencing Z errors, they're now only responsible for looking for Z errors on 2 of their neighboring qubits. So while I've made some of the lazy stabilizers more responsible for the common types of errors, I've made the ones that are responsible for the common types of errors responsible for fewer qubits. So really what I'm doing is sort of lightening the load by applying these Hadamards in this way. Okay, and now look, all these things I've been telling you about, why do you want to, why repetition code is going to give you a better threshold than, say, a 2D error correcting problem. We've just taken the problem of decoding Z errors on this 2D plane, we've mapped it onto a 1D problem. So the thing with the XZZX code is all the Z errors, the common types of errors, they make strings that line up along these diagonals. Any Z error on any qubit will make a string that runs in this direction. It's following the way my mouse is going. And what that means is we can error correct, right? Instead of error correcting the whole 2-dimensional plane of the XZZX surface code, we can break this decoding problem down into a series of 1-dimensional decoding problems. And that, yeah, that's really helpful because it means where before we would have had this 10% threshold for decoding the whole 2-dimensional plane uniformly, by breaking it down into a series of 1-dimensional repetition code problems, the threshold just goes up from 10 to 50%, which is, that's a big improvement.
That 50% is assuming perfect measurements.
Perfect measurements and infinite bias, that's right.
Okay.
But on the next slide, I'm going to tell you about how, yeah, this is, yeah, we assume the more general case. We assume noisy measurements. And then all of this 1-dimensional decoding problem maps onto a 1 plus 1-dimensional problem. So instead of, in the case of the toric code, we started with this 2D code and it went into this 2 plus 1-dimensional thing, shape decoding space. And the threshold went from 10% to 3%. Now at the infinite bias case, we go from having a 50% threshold in this one-dimensional strip to a 10%-ish threshold for this 1+1 dimensional strip. And so the threshold stays really high by still a good factor of a little bit more than 3 higher. And so this is what we plotted here. We looked at bias. Yeah, so you also mentioned that it was infinite bias and perfect measurements. This is now noisy measurements. And these numbers here are noisy measurements. And we plot them as a function of bias as well. So as well as, I've only talked about the infinite bias case, but I'll just ask you to trust me that we can go to finite but high bias decoding problems as well. And it stays kind of one-dimensional, but not quite. It's approximately one-dimensional. So there's a little bit of a hack to make that all work. But what we found was if you go to sensible size biases, where the biases may be Pauli Z errors, dephasing errors occur about 10 times more often than a bit flip error does, or 100 times or 1,000 times more often than a bit flip error does. The threshold compared to the standard case, which is shown by this dark line, it's gone up by, from around 3% to around 7 or 8%. So what we've done is really doubled the threshold. So if you have really good qubits, but you're still fighting to get them below threshold, and we've just made the code have a threshold that's now higher by a factor of 2 or so, then yeah, you're much more likely to be in business. Like making the threshold of your error correcting code go up is gonna making a quantum computer much easier, because that's the bar. You have to get below that bar. You've got to get well below that bar before you're really doing quantum error correction. Right, so that's everything about the XZZX code. I'm at 36 minutes. So
what's the catch? What's the catch? What do you lose as compared to the surface code?
Nothing.
Nothing?
No.
Works as well to find errors?
Yeah, I just took the same code. Yeah, so if you go down to the depolarizing noise case where X's and Z's and Y errors all happen equally, the codes are the same.
Okay.
Nothing.
I thought so. I just wanted to know if I was missing something and if there was a catch.
Well, as I said, all we did was we applied Hadamard's on like alternate qubits. Like it's the same code up to a single unit. Like why would you lose something? I'll tell you what happened. Like I've had this, you can't get a free lunch question before. And here's the thing, like people working in quantum error correction are lazy. So what they like to do is they like to divide this problem up. They like working in what they call CSS codes. And a CSS code is when you have Pauli X and Pauli Z type stabilizers only, in the same way as we have the black and the white chessboard squares. And the reason they like that is because then they can say, well, I'm going to work out how to correct the Z errors separately using the X stabilizers and the X errors using the Z stabilizers. And I'll deal with those two things separately. They don't like going outside of this CSS space. And it made a lot of sense. It makes the calculations easier. It makes solving something. It's like, factorizing the problem in some sense. Yeah, but when you go outside of this CSS world, as soon as you apply some Hadamard's, but it turns out to be really useful for correcting bias noise by quite a big deal. So I don't know. To me, it's like, I like to imagine there was like a big uniform facepalm when people started seeing this paper, but you've not lost anything. It's the same code up to a local unitary rotation. So there are some, what we showed in our first paper on this code is that the threshold, we had a maximum likelihood decoder and we found that the threshold stays, it matches the hashing bound. So the hashing bound is a lower bound on how well you expect random codes to perform, on how much information you'd expect them to send through a channel. And where all the qubits experience noise at a certain rate. And we found that the XZZX code just matched this hashing bound for all single qubit Pauli channels. So that was a big surprise to us. May be of interest to quantum channels and quantum communications. We don't know. It's a numerical observation. It maybe be interesting to prove that that's really true, or find a good use for that fact. We also, we found it even exceeds the hashing bound in some places, which was a big surprise to us as you approach the bias, the dephasing, the infinitely biased dephasing noise point. And yeah, also in this paper, we worked out how to do all the logical gates while preserving these high threshold values that we got for error correcting bias noise. So all these things are good, and we can do all the quantum computation we could with the regular surface code, which was, you know, really all of it with some magic state distillation. But we could keep the high thresholds up as we did these computational operations. So Pablo and I actually went on Australian national television to talk about this because people in Australia got excited by that, and Pablo did this work in his undergraduate, so that's really cool. And right, so that was
a question, if you don't mind. So
sure.
What is the difference between this simulation and the last one? The threshold error rate seems to be exceedingly high.
Oh, so yeah, so when I was talking about the hashing bound, I didn't mention this, but the hashing bound, I don't know how to define the hashing bound when there are noisy measurements. So when I switched over to this slide, yeah, thanks for chasing me up. I went back to the perfect measurement case where the threshold is put 50% at the infinite bias case. And the same was the case here. If you remember, when you just look at the 2D case and measurements are perfect and you're really decoding the repetition code along these one-dimensional lines, the threshold infinite bias is 50% or 0.5. And yeah, as I said, we interpolated between the depolarizing noise case where X and Z and Y all happen at the equal rates, up to the high but finite bias case, up to the infinite bias case. We looked at all these cases, and this is what we plotted. And we compared this with the hashing bound. What we saw is the threshold seemed to creep up above the hashing bound.
I see. So what is the assumptions on measurement error on the slide, two slides ago that you had?
We just assumed that the measurement error rate was the same as the high bias noise rate.
I see.
More or less. So we assume that if you want to measure one of these stabilizers, you take an extra qubit and you entangle it to all of its neighbors, and then you measure that qubit, and that qubit will tell you the value of that stabilizer. Now I'm sweeping details under the rug here, but let's say during that circuit that qubit experienced an error, then the measurement will tell you the wrong outcome. And we assume that qubit would be vulnerable to the high bias Pauli Z error. That's the common type. So measurement error rates are very high.
I see, thanks.
Yeah. But yeah, so the next part that I'm going to talk about is we really simulated. We said, okay, I'm now going to start talking about my work with Shruti and Andrew Damawan.
So far, you've been talking about only correcting errors. Is there anything? What about logical gates?
As I said, we worked out how to do. We haven't got thresholds for those. We haven't got numerics showing how they'll do, but it would be surprising if they're significantly different from the memory thresholds that I've been describing.
And you would do similar things like you do in the surface code, lattice surgery.
You do a lattice surgery, and we wouldn't expect the threshold to change very much. Okay. And as I said, what we checked in this paper, or what we argued, was all of the physics that allows us to get these very high bias noise thresholds. You'll still get to keep those thresholds in the as you're running gates. Even if you do some weird ones where you have twists, but you maybe don't need those ones. You can maybe just do everything with lattice surgery. Right. So as I said, in the other paper that I was going to mention, and I'm only just getting onto it with Shruti and Andrew and Anna and also David, we said let's actually simulate what happens if we run the XZZX code using these Kerr-cat qubits. So now what I'm going to talk about is I'm going to go a little bit beyond the assumptions that I didn't see who asked the question. Actually, I didn't recognize the voice, so I don't know who asked me that. But who asked me the question 2 questions ago, I'm now going to go past my assumptions on the measurement error rates, and we're actually simulating the circuits. So instead of just assuming I can measure an XZZX like this, I actually imagine I put a qubit in the middle of this plaquette and I run this circuit between all of its neighboring qubits. And this is how I'm going to measure those stabilizers. And we're going to simulate those with Kerr-cat qubits sometimes, or just kind of a generic bias circuit noise model that kind of reflects what Kerr-cat qubits are doing, depending on what's more convenient and what we're trying to work out. Okay, so that's what we did. Now, this is an interesting point I'd like to make first of all, because what we found was having an actual bias CNOT gate didn't make a huge difference in threshold. It helped a little bit, but not a lot. So first of all, what we did is we imagined a generic circuit noise model where we run all the C phase and CNOT gates, and they experience an error that might be a bias error model, or it might be not very biased. And what we found, first of all, is if we have bias noise CNOT, bias preserving CNOT gates, so those are CNOT gates that don't introduce a lot of bit flip errors, then the threshold we got was about 2.1%. You could experience an error of about 2.1% on your CNOT gates, and below that number, you'll be in business. But if we didn't use those bias preserving CNOT gates, then the threshold only went down to about 1.7. And that's really encouraging, because there are lots of other platforms where this bias preserving gate might not be possible. Like we relied on, I say we, Shruti and her earlier work relied on the extended Hilbert space of the continuous variable system where the qubit is encoded. And that's not how qubits are always encoded. Maybe you just have transmons or something, and you're not encoding in an oscillator, and you might not have this bias preserving gate available to you. Well, what we found was, don't worry about it too much, because you still get a very good improvement in threshold if you use the XZZX code. The dip is a lot, not so big. And if we compare that to actually running this on a regular surface code, a CSS surface code, the threshold goes down quite a lot more. So there we tried, we looked at running the CSS surface code with the Pauli Z and Pauli X stabilizers as normal. And compared to the 2.1% threshold I showed you on the last slide, you only get more like 1.1% threshold. So we've really increased the threshold by about a factor of 2. So what does that mean? Well, look, we want, as I said at the beginning, the goal of quantum error correction is to make a really good logical qubit. We want to be able to make the error rate of that logical qubit arbitrarily small. We want to compute with them as well, but let's just talk about memory for a moment. We want to make that logical error rate as small as possible. And so if you're at some fixed error rate, say the threshold error rate of the CSS surface code, and you add more physical qubits. So n is the number of physical qubits, and square root of n is the length of this square lattice of physical qubits. Then if you're on the threshold of, say, the CSS code, then the logical error rate shown on the y-axis isn't going to go down as you add more qubits. But the XZZX code, if you're on that error rate, you're already way below threshold. So the logical failure rate is going down exponentially fast. This is a log scale as you add more qubits to the system. So that's what you're getting by having this, using this XZZX code. If your error rates are still quite high, you may well be below the threshold of the XZZX code when you're not below the threshold of all the other codes we've been using. So that's really good if you have a noise bias. So this is the advantage we expect. Right. So finally, and I'm making quite good time, I think. So finally, what we did is, instead of this generic circuit noise model, we actually simulated the Lindblad equation of what noise the Kerr-cat qubits experience using what we know from the experiments that Yale have done. We assumed like the most dominant sources of noise, which are thermal photons and photon loss. We simulated the and we simulated the noise for all of the different operations we need to run quantum error correction. Here's the Lindblad equation for that noise model. We have a thermal photon term, a photon loss term, 2 photon pumping is not a problem. And we plotted threshold plots as a function of kappa photon loss on K, the Kerr nonlinearity strength. And these are the kinds of thresholds we got. What we found was these are very reasonable thresholds to achieve with the with the experimental parameters that are achievable with real physical systems. And I'm now back to the things I don't really know very much about. But I've written down here the kinds of parameters where we could achieve the threshold error rates. We need a Kerr nonlinearity of 10 megahertz, single photon lifetime of 64 microseconds. And I think you compare that to 15 that was achieved on the first experiment, and a thermal photon population of 8%. And this is assuming quite a high bias. Alpha squared is 6, there are 6 photons. That's they had 3 in the first experiment, 3-ish. I think that number is going to go up. Okay, and oh, hang on, I thought I had another. Yes, hang on. I put I added this new slide, but I put it in the wrong place. So let me just say, so this whole program of research is like, what we really want to work out, or what we want to do is like, we want to take these error correcting codes and we want to make the right error correcting code for the kinds of physical qubits we're using to build these things. These these things, these quantum computers. That's what they are. And what we've found, or what we've seen with this example, is that you can, if you know what your qubits are doing, then you can pick the right kind of quantum error correcting code. And what we might also imagine is, well, like, what other things can we do? So this is some recent work with one of Shruti's PhD students called Shraddha, and she's looked at how we could even improve gates, and specifically one of the components of magic state distillation, or that's one of the noisy, resource intensive parts of a quantum computer. And she's looked at how, if you have a bias noise architecture, you can reduce the resource overheads of magic state distillation as we run magic.
When you say high fidelity, how high is its high fidelity?
It's, well, so what we found was, if you're expecting bias noise, we got a p-squared advantage. Like, so what you have to do if you want to do magic state distillation is you put in a noisy qubit prepared in a magic state, which is a plus state with a t applied to it, and that qubit goes in noisy. It goes in with error rate p. But if that error rate p is highly biased towards, say, Z errors, what we found was we could use these bias preserving circuits to detect, we could detect one of the high bias errors very quickly at the beginning, and throw it out if there is a high bias error occurring, or just and try again, or if we don't detect when we put it in. Now that error rate of that qubit we put in has gone from p to p-squared.
Okay.
So like, by doing this quick little error check right at the beginning before you try and build it into your magic state factory, it saves you a lot of time and work later on, because you're just putting in. It's a simple trick. It's a 2-qubit parity measurement. That's all the error detection step at the beginning is. But just by doing that, it saves a lot of time in front. So yeah, I think it's really valuable to look at how we can use the physical features of the qubits we have to do not just error correction and protect quantum states, but also on how to do gates. And this is, maybe we're still just at the beginning of working out the kinds of things we can do by actually working out the quantum error correcting codes and the fault tolerant quantum computations with the qubits in parallel. And there's a huge gap with what people haven't been doing there. So I've got to go back a slide just to tell you the outlook, and we're up to 10 minutes too. So I'm making good time. Right, so yeah, the XZZX code is really good. It has very good thresholds, matches the hashing band, very good fault tolerant thresholds, and it can do, we checked, it can do all the fault tolerant quantum computations, and all we had to do was a Hadamard rotation on half of the qubits of the surface code. And yeah, it became much better at dealing with bias noise errors. And there's still some room to optimize, I think, the Kerr-cat qubits and the XZZX code. We could have done more there, I think. So in fact, the thresholds I've mentioned, they could be better. David, you mentioned leakage. we need to model those types of things as well to continue this program to test really how good this is. And there are two ways of dealing with the leakage. We could actually do, it with, circuitry and like introduce leakage reduction units, which is what a lot of people do, or we could maybe imagine doing it physically. We don't know which one will be better. Maybe they'll be about the same. We could use like 2-photon pumping to get back into the code space if photons misbehave. These things can be worked out, but there's an interesting question there. Do you want to add more circuitry, or do you want to do it at the physical level? And that might depend on your hardware, but these are the kinds of questions we can start asking if we know what qubits we're making our codes with. More generally, here we've just shown one example of how we pick the right code for the kind of noise that we're really experiencing. But in general, what we want is for people who know about how to make codes and people who know about what qubits they have and what the strengths and what the weaknesses of the qubits are. They should be talking a lot more, because this is just one example that seemed to fall out pretty easily. Maybe there's lots of room to keep finding better codes for the kinds of qubits that people are really making in the lab. And I think that's quite an exciting idea. It's not been explored very much, and it just might make it that much easier to build a quantum computer. So I think with that, my last slide is my collaborators one more time. Thanks for your attention. And that's all I have to say.
Let's clap virtually for Ben. And in the last 5 minutes, does anyone have any questions, comments, etc.?
Yeah, I have a question. I enjoyed your talk, so thanks for the nice talk. My question is about the Kerr-cat qubits. They tend to have you have a large bias, but it means that one of their energy relaxation rate is pretty slow, and then the phase flips, they tend to happen quite frequently. But what would happen if I had a qubit that had the opposite problem? So would your results for the XZZX code still apply, or how does that result transfer?
So what I showed with the over here, the XZZX code is actually good at dealing with any kind of bias. Like high bit flip bias is okay, high Z flip bias is okay, or Y flip bias is okay. You can also try and change the bases of the state. Like you could imagine the XYYX code instead of XZZX if that might be more suitable for the types of noise. That's what we were working with for a while. We replaced the Z stabilizers with Y stabilizers, and we were doing quite well with that. But then the XZZX code would do quite well. It would do better, in fact, at the right types of bias. Where we had different ways of decoding these things as well. Yeah, as I said, I think there's a lot of room to look for the right codes for the right types of noise models.
Have you looked at applying this XZZX code to different types of qubits?
So that the first slide I showed you of thresholds, these weren't really, these are more sort of generic noise models. We dealt with the noise model at the level of the circuitry. So we for every C naught we used and every C phase gate we applied some errors, and sometimes they were high bias errors and sometimes they weren't. But in principle, I don't know how to do quantum computing if you're not doing it with the circuit error model. So in principle, these thresholds are kind of generic. If you actually want to know, if you have a qubit in mind, I think all you can do is what we did here, and you just simulate the Lindblad equation for the types of noise you expect your qubits to experience, and then see how they do this way. But you can only really do it one at a time, and this was quite difficult to do because it took a lot of work. Like in practice, Shruti was running the Lindblad equations and turning them into Pauli error models, and then sending them to Andrew, who was doing all the quantum error correction work. And so this is why with this generic noise, we were able to take a lot of data points because you just change one parameter in the code and it will do a new noise model. But for each of these data points, a different Lindblad was simulated with this changing parameter to get all the to get all the Pauli error rates out correctly. I think if you look in the paper, you can see the tables of what the error rates are for each data point. But yeah, no, we did Kerr-cat qubits. You can do it with any others, but it's a bit of a project, and it means working out one by one, really.
Thank you.
Okay. And any other questions? If there are no more questions, let's thank Ben again. That was a very interesting talk, Ben. I enjoyed it.
Yeah, thanks for all the questions during the talk as well. It's been fun.